Hello everyone, and welcome to today's chem lesson. Today we are going to talk about the idea of intermolecular forces, which is a step back from the bonds and the bonding that we have looked at so far this unit. Bonds exist inside of molecules. So if I draw a molecule here, CH4, the bonds are inside this molecule. That makes them intramolecular forces existing within the molecule. Intermolecular forces are what we look at when we take a step back and see how this molecule interacts with other molecules, either the same or different. How these two molecules are going to interact is an intermolecular force. Same thing goes for these molecules, these molecules, these molecules, right? We're looking at the interactions between multiple molecules and no longer looking at the interactions between atoms to make a molecule. We're taking that step back to look at these forces. Now, there are three different types of intermolecular forces, and we're going to look at them from weakest to strongest. Dispersion forces are the weakest intermolecular force, followed by dipole-dipole, that's our medium intermolecular force, and then hydrogen bonding is our strongest intermolecular force. Now, when we look at a dispersion force, when we take a look at these three forces in order, we'll look at dispersion forces first. A dispersion force is basically just the weight of the other molecules pushing down on each other and any interconnectedness that those molecules may have, right? Any tangledness of those molecules. So, some real-world examples, right? It is gym class, and you walk over to the place where all of the balls are stored, and you have to pull out one ping pong ball from this big bowl or big box full of ping pong balls. Alright, you notice that there's one down here at the very bottom that's a cool solid red color while all the other ping pong balls are white, and you're like, I like red, I want the red one. And so you reach down and you pull out that ping pong ball from the very bottom. Not a very difficult thing to do. Right? Ping pong balls don't weigh that much. They're not going to get in your way all that much, right? You could just reach your arm all the way down, grab that ping pong ball, and pull it out. Now, what if these are basketballs? What if you have to pick one basketball out of this bin full of bigger basketballs? Now that the things you're interacting with are bigger, bulkier, it's a little bit harder to reach all the way down to the bottom to pull out this particular basketball. They're not attached in any way, right? The basketballs and the ping pong balls, there's no difference between them, right, except size, but they're not glued together, they're not stuck together, they're just stacked one on top of the other. Now, what if these are bowling balls? And you have to reach all the way down to the bottom to get your favorite bowling ball out of this big bin full of bowling balls. You see how that's even more difficult than the basketballs or the ping pong balls. And yet there is nothing attaching these basketballs, bowling balls, ping pong balls. There's nothing attaching any of them together. They're not glued together. They're not magnetic. They're not sticky. Right? They're just stacked on top of each other. Those are all dispersion forces. The strength of those forces increase as you get bigger and heavier molecules. Right? The bowling ball, this bottom bowling ball, is the hardest thing of our three examples to remove, because the other bowling balls push down on this one a lot. right? That interaction, even though there's no difference between these bowling balls, ping pong balls, basketballs, the weight, the size of those molecules makes a big difference. Now, all molecules, every single molecule has dispersion forces. Every single molecule, no matter what. But nonpolar molecules, molecules that are symmetrical, molecules where the electrons are shared equally, nonpolar molecules only have dispersion forces. They cannot have any stronger type of interaction. They're not going to have dipole-dipole forces. They're not going to have hydrogen bonding. It's not possible for them because they do not have dipoles, which is something we're going to talk about in a second. So every molecule, no matter what, has these dispersion forces. They get stronger. The bigger the molecule, the heavier the molecule. And nonpolar molecules only have access to these dispersion forces. Now, let's take a look at a practice problem. Of these 4 nonpolar molecules, which one of them has the strongest dispersion forces? Here's a little snippet of the periodic table for you. Which of these has the strongest intermolecular forces? Which one of these has the strongest dispersion forces? The only way we can tell the difference between things that all have dispersion forces is we're looking for the biggest and heaviest molecule. Using our trends from the periodic table, we know size increases as you go down a column of the periodic table. And so that makes iodine our biggest, heaviest molecule. It means it will have the strongest intermolecular forces of the bunch. Now, what if it's a polar molecule? What happens to polar molecules when they interact with each other, right? How do their intermolecular forces work? Let's take a look. For a polar molecule, you have a dipole-dipole interaction. And a dipole is the thing that is formed by a polar bond. This bond, let's change font color to keep things interesting here. This bond is a polar bond. This and this hydrogen and this sulfur are not the same thing, which means that these electrons are not going to be shared equally. Now, that uneven sharing of electrons leads to a dipole. It leads to electrons being bunched up around this sulfur. The sulfur is better at pulling. It shares unevenly with these hydrogens. It has a bigger percentage of the electrons closer to it. And that makes it sort of negative. Right? It has pulled those electrons closer to it. Which means if this is sort of negative, these hydrogens are sort of positive. Not a full positive. They haven't gained or lost electrons, right? The sulfur hasn't gained electrons. The hydrogens haven't lost electrons. They're still sharing. It's just not very even. It's just not very good at sharing electrons. And because of this semi-charge that exists now, when I put a bunch of H2S's near each other, the S is going to be attracted to the H. The H is going to be attracted to an S. And so on top of the dispersion forces that these things have, right, on top of the fact that they're stacked one on top of each other, there's also this magnetic attraction that exists between the sort of negative side and the sort of positive side. An extra little thing holding these together. That is our dipole-dipole interaction. It is a slight magnetic attraction on top of the fact that they are weighing each other down by being stacked one on top of each other. Now we see I'm going to trace it, this symbol, this long arrow with the tail at the end. And that's a symbol we see when we look at a line of symmetry in a nonpolar bond, in a polar molecule. So if we look at our molecule, we draw our line of symmetry, if there is one. The arrow points to the sort of negative side, and the little plus sign shows the sort of positive side. Not the most common symbol in the world, but it is present in some textbooks, some diagrams. You'll see them if you're doing any reading outside of class. Now, if this is a medium strength intermolecular force, right, it shows the stacking and this slight magnetic attraction. Hydrogen bonding is a stronger dipole-dipole force. It's the exact same concept. It's still this sort of negative and sort of positive interacting in this way, but the dipoles that are formed in a hydrogen bond, H connected to F, or H connected to O, or H connected to N, those are the three strongest dipoles. So strong that they get their own category. They get this hydrogen bonding category. It's still the exact same idea. If I were to draw something like water, which features one of our three bonds, right? That's H connected to O. And we look at the bunching, come back here please. We look at the bunching up of the electrons, sort of negative, sort of positive. It's still that same idea of a dipole, but now these are stronger. If we compare it to our H2S, the sort of negative that's here, let's say sort of negative 0.5, and sort of positive 0.5. Here, we still have that sort of negative, sort of positive, but here we've got stronger charges. And so it's the exact same idea. It's these magnetic attractions holding these molecules together on top of the fact that they are stacked one on top of each other. But this magnetic attraction, the magnetic attraction of HF, HO, or HN, is stronger than any other dipole-dipole force that exists. Both of these are dipole-dipole forces. Hydrogen bonding is just the strongest, so strong it gets its own name, right? Both of these are movies, but only water has won an Oscar, right? Just so much stronger than another movie. both of these are athletes, but only water is an MVP. Or whatever analogy you want to use here, they're the same, except water is better. Right? This hydrogen bonding is better. It is stronger. And it's going to lead to stronger intermolecular forces. If we want to take a look and kind of summarize this, we can summarize in a little flowchart. To find out what intermolecular forces something has, all we really need to do is ask two questions. The first question is the molecule polar? If you're looking at a molecule and you say it is not polar, this is a nonpolar molecule, you can move right down here. A nonpolar molecule only has dispersion forces. This is the only possibility for a nonpolar molecule. If the molecule you're looking at is polar, you have to ask a follow-up question. Does it have H connected to F, H connected to O, or H connected to N? If it does not have HF, HO, or HN, it is a polar molecule with dispersion forces and dipole-dipole forces. There's a magnetic attraction, but it's not one of the three strongest. If it does have HF, HO, or HN, it goes down here to a molecule that has dispersion, dipole-dipole, and hydrogen bonding. All three are present in polar molecules with H connected to F, H connected to O, or H connected to N. And so by asking those two questions, you can pretty immediately tell what category you fall into and what your bonding is going, or what your intermolecular forces are going to be. Now, let's try this in practice. Of these three molecules, which one of them has only dispersion forces? Now remember, you should be able to draw these on your own. So I'm going to draw this first batch for you, and then give you a little extra time to make sure you get your drawings down correctly. If a molecule has only dispersion forces, something that has only dispersion forces, we're looking for a nonpolar molecule. A nonpolar molecule has multiple lines of symmetry. There's only one line of symmetry in choice 1, only one line of symmetry in choice 3. But choice 4, we can draw multiple lines of symmetry. We could draw up to 4 lines of symmetry, making it nonpolar, meaning it is the only one of these three that has only dispersion forces. All three of them have dispersion forces, but the only one that has only dispersion forces is choice 2. What about this one? Which of these has dipole-dipole interactions? I'm going to let you draw these ones out on your own. Actually, no, I'm not. If you want to draw them out on your own and get that practice, pause the video here, draw them out. If not, pause it after I draw them. which one of these has has dipole-dipole interactions, not only, just dipole-dipoles. Here, if we're looking for something that has a dipole-dipole interaction, we are looking for something that is polar. So it's the almost opposite of what we asked before. We have multiple lines of symmetry in choices 1 and 2, but actually no lines of symmetry in choice number 3. So choice number 3 is a polar molecule, which means it has dispersion forces and dipole-dipole forces. Choice 1 and 2 have only dispersion forces because they are nonpolar molecules. Choice 3 also has hydrogen bonding. It's got an O connected to an H. That doesn't change our answer. Right? You can have all 3 intermolecular forces, but this one's asking which one has dipole-dipole. Choice 3 is the only one that has dipole-dipole. What about this one? Which of these molecules has hydrogen bonding? Again, if you want to practice your drawing, pause. I'm going to draw them, and then I'm going to pause again to let you answer. Right, so your drawings should look like this. Right, which one of these has hydrogen bonding? For a molecule to have hydrogen bonding, we are looking for 2 things. We are looking for a polar molecule, and we are looking for HF, HO, or HN. Choice 2 is a non-polar molecule, which means it has only dispersion forces. So it's not choice 2. Choice 3 is a polar molecule, so that's on the right start, but it does not have HF, HO, or HN, which means it has dispersion forces and dipole-dipole forces, but not hydrogen bonding. Choice 1 is polar, so it can only draw 1 line of symmetry, and it has HF, right? It's only H connected to F. So it has all 3: dispersion, dipole-dipole, and hydrogen bonding. It's the only one of our choices that has hydrogen bonding, so it is our answer. Now, how does this come into play in the real world? It actually connects, interestingly, back to melting points and boiling points. Things with strong intermolecular forces have high melting points, high boiling points, low vapor pressures. Things with weak intermolecular forces have the opposite: low melting points, low boiling points, higher vapor pressures. And the reasoning for this is because of that strength of attraction within the molecules. Since they're being held more strongly together, it's difficult to force them apart, right? To melt something, you need to force those molecules away from each other. To boil something, you need to force those molecules away from each other. When something evaporates, those molecules are going to spread away from each other. So the stronger the intermolecular forces, the harder it is to make those things spread out. The weaker the intermolecular forces, the easier it is to force those molecules to spread out. And so we get this interesting connection where things with weak intermolecular forces have low melting points, low boiling points, and high vapor pressures, and vice versa. And with that, I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.